Welcome to this year's Royal Academy of Engineering Research Forum. It's a great pleasure to see so many of you here today. We've got quite a few more registered who no doubt will be turning up during the morning. I'm Ric Parker. I'm Director of Research and Technology at Rolls-Royce. I also have the pleasure to be the Chairman of the Royal Academy of Engineering Research and Secondments Committee that looks after the awards of our fellowships, sponsored chairs, etc. And the team here in the Academy have been responsible for pulling together today's agenda. I must admit I've had very little direct input, but have been able to poke it in one or two of the right directions, I hope. Because as you'll see from the layout, we're trying one or two new things this afternoon. We value your feedback on what works and what doesn't work. It's my pleasure to welcome you here to Prince Philip House. Those of you that haven't been before, take a look around our new building, or at least our newly refurbished building, and it really does provide an excellent space for such events compared to the facilities we've had in the past. In fact, for many years we used to go off-site for this meeting because we just didn't have a room big enough to hold it ourselves. The obligatory health and safety and housekeeping matters, we're not expecting any fire alarm tests. Therefore, if you do hear a fire alarm, take it seriously. Use the fire exits, which are all clearly marked in this room. Do not use the lifts. If you need assistance and cannot use the stairs, then make sure one of the Academy members of staff knows that. I suggest, unless smoke and flames are coming from that direction, the easiest route out is out that door and down the main stairs, and then head out the front of the building and turn left and assemble somewhere near to the little roundabout at the end of the terrace, and that way you'll be not mown down by the impending fire engines, so you'll be kept safe. If you could just check, and I reminded myself to do it myself now, usually at this point somebody rings me just to remind me, could you preferably turn your phones to off? If you are expecting something of life-threatening importance, then at least have them on silent during the event, although even on silent they can sometimes interfere with the sound system electrics. Those of you that may doze off at any point and want to refresh your memory on what you might have missed can catch up. The whole event will be put online on range.tv.com, so take a look at that, and you'll be able to see pictures of yourself snoozing and therefore recognize the bits where you may have dropped off. This year's research forum is happening during perhaps an unprecedented period of analysis and understanding of the challenges that the country faces, some signs of emergence from past troubles, but much more to do in terms of growth, and particularly still the grand challenges around us, both social, environmental and technical. And we as an engineering academy and you as engineers can play a huge part in fueling that future growth, and some of what you see today I think will give you insight into some of the very impressive work that's happening that may facilitate that. There are a number of major policy initiatives underway as we run up to an election year, and the Academy has been very active in supplying input to those, supplying comment, and through both our policy committee and the research committee. We see around us an ever-growing list of 8 great technologies. I think we're up to about 11 or 12 great technologies now, but it's welcome that key technologies for our future are recognised by the government. There's a long-term plan for capital, which will set out a roadmap for research infrastructure investment of the order of 1.1 billion a year over the next few years, and that's hotly awaited, and again the Academy had its input to that. And we're looking forward to the publication of the Science and Innovation Strategy, which will come out alongside the capital plan. We've consistently called for a stable and long-term planning environment for research and technology and engineering in the UK, and I think we're starting to see some promising signs of that. Notwithstanding, as I said, the fact it will be an election year next year, but we've seen commitments by this current government that certainly exceed their immediate span of residency in government. A good example is the Aerospace Technologies Institute, a 7-year commitment, £2 billion in total for research in aerospace, coming 50-50 from industry and government. So, as I say, promising signs that we have a government at the moment that's willing to think and commit on a long-term basis. As an industrialist, I welcome many initiatives that are helping to promote collaboration between university and industry, and the Academy is not backward in doing that. Most of our research funding, and certainly all our research chairs and senior fellowships, have to have an industrial partner as part of the package, and that's vitally important. Our research chairs are jointly funded, as I said, and are in a very efficient and effective mechanism. For every pound the Academy puts in, we can track value creation of 10 more pounds through input from industry, through input from the universities themselves, which are normally quite generous in supporting the Academy initiatives. And it's a very efficient funding mechanism. And I think BIS, who ultimately give us those funds to distribute, recognise that we play a unique role that doesn't just duplicate the much larger funds that go direct to the research councils, but does something special, something unique, and something very effective. Our research fellowship continues to be one of the most sought-after awards for early career engineers, and the scheme currently provides 53 high-caliber early career researchers, and you'll hear from one or two of them today, and moreover the poster exhibition has many more examples with the keen poster presenters standing by them to help explain. 7 new appointments were made in the past year, and it's a highly competitive field. We have many, even at the pre-SIFT level, we had over 80 applications, and that's brought down to a short list from which those 7 were selected. So had we more funds, and we did in last year's review seek more funds from BIS for the research side of the Academy's activity. Unfortunately, in the current climate, we didn't get it, but had we more funds, we could create many, many more high-quality fellowships. In recent years, the Academy has increased its focus on commercialization of research, and this afternoon's session will talk about the impact of research and how we measure that. In particular, last year the Academy established its Enterprise Hub, which is physically down in the basement here, but a much wider network of fellows and people helping young entrepreneurs and even older entrepreneurs to get their ideas off the ground and bring them to the market. And for the first time, as part of the forum today, we'll be hearing from one of the Enterprise Fellows in this morning's session, so I look forward to that. Another important development in government circles has been the creation of the Newton Fund, £375 million for helping to establish research. It's come out of the aid budget, so it has to be spent in a list of 12 or so overseas countries to establish research infrastructure, establish research quality, establish research capability. And the Academy is one of the delivery partners for that fund, and so has a direct say in how a proportion of the total will be spent. And again, I'd encourage you to engage with the Academy. It's all come together quite quickly, and there's quite a rush to spend some of the money before next Easter. But basically, if you have already strong links or are looking to form strong links with China, India, or other countries, largely in the Asia and Southern America, then it's an opportunity to get those links funded, to have exchanges in both directions, so researchers from those countries can come here, funded by the Academy, or people from the UK can go to those countries to help with the general theme, as I say, of building research capability in those countries. The heart of the Academy is obviously its fellowship, now numbering 1,500 or so, and again, it's a great pleasure to see so many of our fellows here today. The fellows play a pivotal role in the research activity. A number of them sit on my committee and help directly direct the research budget and the recipients of our awards. A number of others man the panels that judge the individual recipients and help to sift them down from these longer list of hopefuls. And many more act as mentors. And again, a unique element of our scheme is the mentoring we give to the people who win our fellowship. So they don't just get a pot of money and tell, come back in 5 years and tell us what you did with it. They get active support from key people in the fellowship who are already experts in similar fields. I'd just like to pay tribute to the industrial sponsors of the awards, many of whom are here today. Without them, obviously, the scheme wouldn't work. And again, I think an interesting change in the last couple of years is we're seeing more SMEs coming forward willing to sponsor PhD, sponsor fellows and even chairs. And that's a welcome diversion from the past when it's mainly been larger companies, but we still nonetheless do value the input from the larger companies. Finally, I'd like to acknowledge the support that the Academy does get from BIS. As I say, we never feel it's enough, but we would always say that irrespective of the amount involved. I'm very pleased that Professor John O'Reilly is actually taking a break from his holiday to come and talk to us this afternoon. So John will arrive at lunchtime and will then go back to join his family for the rest of his holiday. But I'm very grateful to John for being willing to do that today, and we look forward to hearing what he's going to say. Our ambition as an academy is to support the very best researchers to carry out world-class engineering research for the benefit of both industry and the society at large. And today's forum, I hope, will demonstrate that we're doing exactly that. Just in completion, just run you briefly through the structure of the day. The morning follows the usual structure where we hear from current recipients of the awards. We also like to hear from past recipients so that we can get that retrospective on how an award from the Academy may have helped them in their career and helped them get to the position they're in today. So 4 speakers this morning spanning our full range of awards, and as I said earlier, one of our very first enterprise fellowships. Afternoon, we'll then break for lunch, and I say during the breaks do take every opportunity to view the posters, see what's happening downstairs, and there are also some tabletop exhibitions with hardware and things to play with. Lunch and again the poster exhibition will be around 12 o'clock, then be back up here promptly, and we have John O'Reilly talking to us. In the afternoon, we've done something slightly different from the previous time. Instead of just having the recipients of the awards, we've invited both the recipient and the industrial sponsor to do a double act in 2 presentations. So we can hear from the industrialists why they do it, what they seek to get out of it, and how it helps them to have fellowships or sponsored professorships with their company's title associated with it, and their company receiving the benefits of that research. And then in the latter part of the afternoon session, we will have a panel discussion on research impact, again very topical, the outcome of the REF intimately awaited. We have people who've been directly involved in the REF on that panel. We have people who will be the customers for its output, and we'll be exploring whether the current move to pay more attention to research impact is a good thing, whether it's adding value, and indeed whether we have a common understanding or definition of what research impact should be and may be. So a very full day, and for those of you who don't have to rush off to start your weekend, then at the end of the day there'll be a drinks reception, which I hope the majority of you will be able to stay for. So without further ado, and already past my allotted time, I will introduce our first speaker. The first speaker is Paul Shearing. Paul is a Royal Academy of Engineering Research Fellow, awarded that starting in 2012 at University College London. He's Senior Lecturer in Chemical Engineering, and he has a first degree in Chemical Engineering from Birmingham. He completed a PhD with the Department of Earth Sciences at Imperial College and also won the PhD prize in 2010. And Paul is going to speak to us today on 4-dimensional tomography of electrochemical devices. So, Paul, welcome, and the floor is yours. If you'll excuse me, I'm going to sit down there so I can see the screen.
Thank you very much for the introduction. Thank you to the Royal Academy of Engineering for the invitation to speak today. I'll be talking about my research fellowship, which is four-dimensional tomography of electrochemical energy devices. Excuse me. As mentioned, my Royal Academy of Engineering fellowship runs from 2012 to 2016, and so at this point I'm roughly just past the halfway point. I thought that it was useful to start with some of the goals of the fellowship when I wrote the application in sort of 2010, 2011. This was to explore the application of three-dimensional imaging, tomography, to fuel cells, batteries, and other electrochemical devices, with a view of understanding how the microstructure of the materials that build up these devices affect the device performance and affect how the device will age, degrade, and fail. This is where the 4D element comes into the imaging. That is 3 dimensions in space and 1 of time. The dimension that we use in time is to explore how the structures will evolve, for example, in response to long-term aging and corrosion, but also in response to extreme environments such as temperature, pressure, etc. We're using multiple length scale techniques and indeed multiple modalities to understand these devices in what we like to think of as an atom-to-device approach. The scope of the fellowship is quite broad and much too broad to cover in 20 minutes this morning. So in today's talk, I'm going to focus on a key question, which is how can we use X-ray microscopy to design better electrochemical devices? And by better, I can mean a variety of things. That could be safer, longer lasting, it could be higher power or energy density, and indeed it could be the use and application of new materials. Before beginning, I thought it was worthwhile for this audience to define exactly what we mean by electrochemical energy devices. At UCL, we have research spanning a broad remit of electrochemical technologies, from fuel cells, lithium-ion batteries, which we use on a regular basis, electrolyzers, redox flow batteries, a very broad remit. And historically, these have been applied in a variety of different applications. Driven by the space program, much of this work, it continues to feature in a number of aerospace, both as primary movers for example, a Boeing fuel cell powered plane, which launched in about 2006, as well as for auxiliary power units. And of course, with the Boeing Dreamliner incidents, we're all very conscious of the application of lithium-ion batteries and their safety for aerospace applications. Marine applications, there are solid oxide fuel cell powered submarines operating in both the Italian and German navies, maybe slightly more niche applications in the leisure market. Automotive research drives an awful lot of the interest, particularly from our students who approach these problems because they want to build better fuel cells to go into cleaner cars. And we work very closely with companies, including General Motors, to explore how we can improve the design of electrochemical devices for automotive applications. From the sublime to the somewhat ridiculous, there are people who propose fuel cell tractors. These haven't gained any traction in the market as yet. Similarly, the fuel cell-powered lawnmower is not available in your local DIY store, although some of you will notice that battery-powered cordless lawnmowers are now relatively commonplace. One area where fuel cells are gaining a significant market share is in the niche application of forklift trucks. Stationary power units, both redox flow batteries, large-scale batteries, and fuel cells have a significant role to play there. And of course, consumer electronics, where we all, every day, walk around with a lithium-ion battery in our pocket for the most part. So the lithium-ion battery that we walk around in our pocket is a highly energy-dense material. I wanted to explore what happens when things go wrong. This is an image which, unfortunately, appears to be not quite playing as hoped, but is a thermal image of a lithium-ion battery that's rotating very quickly as it's being heated, causing some thermal runaway effects to become initiated. The scale on the right-hand side is in degrees centigrade. This is an infrared thermal image, and you can see that the battery becomes hotter and hotter and hotter, causing a number of exothermic reactions to occur. And as these occur, we initiate a process which is a sort of runaway thermal process where things snowball, and eventually you get these explosions. This is what's called an 18650 battery. So an 18650 battery is typical of one that you would find in a laptop. These are 18 millimeters in diameter, 6.5 centimeters tall, just slightly bigger than an AA battery. And you can see that the energy density that's contained within one of those laptop batteries is significant enough to cause a relatively violent explosion, some heating in excess of 260 degrees centigrade there. To put this into context, if we take the scaling from an 18650 cell, such as you'd find in a typical laptop, and apply that to see what it would look like in a electric vehicle, the original Tesla Roadster Mark I had just close to 7,000 of these 18650 cells in the car. This was actually off-the-shelf 18650 cells, which they sourced from a company in China, and they put 7,000 of these into the automotive powertrain. I think that the engineers in the audience will probably question the wisdom of the engineering design behind that, but the economies of scale were such this was the only economic way of doing it. Even with the economies of scale, the lithium battery pack was close to sort of £50,000 or so in the cost of those cells. But of course, when you've got something that's something of that scale, the implications for failure can be much more severe. So catastrophic failure here, a famous picture that was circulated of a Toyota Prius range extender that had exploded. Similarly, the Japanese Boeing Dreamliner that grounded the entire 787 fleet because of the lithium-ion battery. We're all very conscious of exactly what the consequences of these battery failures are. And from the National Transit Safety Board, this is the exact battery that brought that plane down, the 787. I was interested in reading their safety report that they'd also moved towards X-ray imaging to understand exactly what happened within these battery cells and used it as a post-mortem diagnostic tool. And you can see that there is a stacking there of 8 different cells within that bomb-proof box that have obviously undergone some thermal event leading to explosion. And I was struck also when reading this. This is extremely similar to some work that we published about 3 years before, warning about the dangers of high-density lithium-ion polymer battery packs if they're not installed correctly. And in fact, the X-ray images that we're scrolling through here show a very similar picture into how these electrodes and these device architectures fail, sometimes catastrophically. So this was a laboratory computed tomography X-ray image, and I'll come to the fundamentals of X-ray imaging in a couple of slides. Image of a battery similar to the Dreamliner after the failure event had occurred. One of the main goals in this fellowship, which is a 4-dimensional tomography approach, is to understand the events that lead up to this failure, understand how the electrodes change, how the devices change, degrade and fail, with a view to then obtaining some insight into new approaches for engineering design to make safer batteries, to make more durable batteries, and also apply that to fuel cells, electrolyzers, and so forth. As I said, today's talk will focus on lithium-ion batteries. And so quickly to look at the fundamentals of what we've all got that powers our laptops and digital cameras and mobile phones and so forth. A lithium-ion battery has an anode and a cathode. The typical anode material is graphite, which acts as a host for lithium in the charged battery. During discharge, lithium will move from the graphite anode into normally an oxide cathode, for example, an olivine structure or lithium cobaltate, and then the process is reversed during charging. These SEM images give some insight into what the 2-dimensional structure of these battery materials look like. They're highly heterogeneous, they're highly complex, and really an amazing piece of engineering to be able to build an 18650 battery for your laptop or for your digital camera and sell it at a profit for kind of $9 or $10, an enormous amount of engineering that's gone into those materials and devices. The research motivation was to understand these materials from the atom to the device level. And the reason we're using a tomography approach is to get a 3-dimensional picture of these materials. If we look again in more detail at the image on the left, this is a lithium-ion battery cathode material. A 2-dimensional electron micrograph gives us some information that kind of gives us a qualitative picture of what these materials look like. Historically, all of the investigations pretty much that we've had have been 2-dimensional, and whilst they remain a valuable tool for analysing materials, because the materials are highly complex, because the heterogeneities are linked to 3-dimensional materials properties, 2-dimensional information is not enough. We need to understand these materials as a prerequisite in 3 dimensions. Furthermore, whilst I will focus today predominantly on the experimental tools we use to characterise these materials in 3 dimensions, modelling and image-based modelling is paramount to understanding the performance of these materials. We can use image-based models such as the mesh-based approach on the left-hand side to combine the tomography data we get from X-ray imaging with relevant simulation tools and understand the existing suite of materials and their microscopic performance, and of course then this feeds into designing a new generation of battery electrode materials. A quick view of exactly what the X-ray techniques that we're using look like. X-ray computed tomography that we use in material science is based on exactly the same principles as a CAT scanner that you would get in a hospital, whereby we have an X-ray source, a specimen which is rotated relative to the source and the detector. We collect a sequence of images as we rotate that sample, and these come out as shadow images, such as the image on the left-hand side. And using some back projection mathematics, we can reconstruct these shadow images into a slice-by-slice image of what the internal structure of the material looks like. There are a number of different flavors of X-ray CT instrument that I will show today, and predominantly it is differentiated by the resolution that they can obtain, the source that they use, whether that's a laboratory source or whether that's a synchrotron source, and corresponding to that, how fast we can capture the tomography data. Lithium-ion batteries represent a fascinating problem for anyone interested in multi-length scale imaging, because we find that from the millimeter down to the nanometer length scale, we have material science, materials engineering, and device engineering challenges ranging from introducing new particle morphologies and new chemistries through to how we should design coin cell architectures for medical implants, and then finally at the coarsest length scales, understanding exactly what those cell degradation events look like and how they occur. As I said at the very beginning, we use a suite of microscopy tools, including electron microscopy and focused ion beam techniques, but predominantly we're focused on X-ray microscopy, and those are the results that I'm going to present today. X-ray microscopy is nicely summarized in this slide, which is from a recent paper by Phil Withers from Manchester, which looks at a range of different tomography platforms based on the spatial resolution that you can achieve and the time in which you can characterize these materials. Because we're interested in four-dimensional tomography, sometimes we need to go to very, very fast tomography instruments in order to be able to characterize the extreme dynamic processes that are associated with failure, such as the one that you saw in that thermal video at the beginning of the talk. So why are we using X-ray images to study these energy storage materials? Well, there are some key performance issues. The failure mechanisms we've already discussed. We are all conscious of the lifetime degradation of our laptop and mobile phone batteries, and ideally we'd have an improved capacity because we want to charge these less and less frequently, particularly for automotive applications. That's a rate-limiting step in their commercialization. The imaging requirements are that should be non-destructive, penetrative. It should give us some good contrast across a range of different resolutions, which enables us to go from device architectures down to microstructures, and in fact down to the very fine length scale that's associated with chemical decomposition. In the remainder of the talk, I'm going to pick up a few examples from each of those different areas. So first of all, if we look at a very standard primary battery, this was a very similar battery chemistry to one of the failure events that was associated with the Heathrow Dreamliner incident, which was slightly different to the Japan Air one. And at the cell level, we've utilized laboratory and synchrotron tomography to characterize the changes that are occurring inside this battery at the electrode and the device length scale. So for those of you that have never seen inside a battery before, this is typically what an AA battery or a CR2 battery looks like. They're kind of Swiss roll type structures, or jelly roll structures, as the Americans refer to them as. And we've been able to use X-ray imaging as a non-destructive tool to track the changes within this battery as a function of state of charge. So here's a slightly zoomed in image where we can see the electrode rolls in this kind of jelly roll formation. The bright spots are the current collector, a mesh-based current collector. And I'll ask you to focus onto this red box and highlight some changes that we can take and understand as we take tomography sequences during the state of discharge. So we're discharging the battery. As this discharge is occurring, we're seeing swelling of the electrode layers, which is what we'd expect, but if I play it one more time, we're also seeing the development of significant cracks within this electrode layer. The development of these cracks will have a number of effects that we're modeling at the moment. The first effect is that actually it might help you to discharge your battery more quickly because you will have more facile ion transport. The second effect that's perhaps more worrying is that you'll have localized current hotspots. The localized current hotspots are going to give you a temperature source. The temperature source is potentially going to be an indicator of the initiation of the thermal runaway effects that we saw at the very beginning. So by using these penetrative, non-destructive techniques, we're able to now explore in near real time exactly how these batteries are performing and propose some mechanisms by which they may fail, and then consequently come up with engineering design solutions to understand how we may make safer batteries. In another example, we've looked at a Panasonic battery, which is about 4 millimeters in diameter. These batteries are used for a range of memory backup devices, but also for medical implants as well, for pacemakers and so forth. We've utilized non-destructive lab-based CT in this occasion. The previous occasion was using a synchrotron. Here we've used lab-based CT to characterize changes in the microstructure in this battery, again non-destructively, and link it to the performance electrochemically of the battery. This short video explains exactly how the experiment was conducted. So we have an X-ray source here, and this battery, to give you a picture, is about 4 millimeters across, as I say, something that would typically go into a pacemaker. This was we were very pleased that this was a featured cover image in a recent article in Advanced Energy Materials. So using the X-ray technique, we can obviously non-destructively characterize the materials. So we can strip away the can virtually to understand exactly what the electrode layer looks like. This is a coarse level scan using a 5.6 micron voxel. A voxel is a volume pixel, so a three-dimensional pixel. And if we zoom in and we superimpose some higher resolution data here, so this is about 1.2 micron voxel data or 1200 nanometer voxel data, and we're beginning to understand non-destructively and in detail exactly what the particle morphology looks like within this cell. In tandem to this, we're also conducting electrochemical characterization, again with the key aim of linking the microstructure of this electrode device to the electrochemical performance. And those last slides just showed slice by slice exactly what that electrode material looked like. So if we reconstruct the 3D image and sort of take a cross-section, we can see here that we've got a manganese-based cathode material. We can see that we've got a lithium aluminium negative electrode. And as we charge and discharge, we get dilation and erosion effects that are occurring in the materials during lithiation as the lithium is transported to and from the cathode, basically. If we zoom into exactly what the cathode material looks like, we can identify individual grains. We can also identify defects within the battery space. We can also look at cracks within the negative lithium aluminium electrode as well. By tracking how these grains and these particles and this morphology of the device move and reorient as a function of state of charge, we can use a technique known as digital volume correlation, which is three-dimensional digital image correlation, in order to map the displacement of the battery as a function of the state of charge. We can also use particle tracking algorithms to track on a particle-by-particle basis exactly how these particles are eroding and dilating, moving, reorienting as a function of the lithiation of the device, and therefore as a function of the state of charge of the overall battery. And this was the first time that we were able to directly link the microstructure to the electrochemical performance. If we extend these experiments over longer periods of time, we can look over 50 charge cycles, 100 charge cycles, 200 charge cycles. Again, crucially, this is a non-destructive technique, so we are empowered to do these four-dimensional studies in a completely non-invasive fashion. We can begin to image the effects of aging, and again, we've identified pore widening effects, hoop cracking effects, and so forth. That gives us an insight into how we might engineer the devices, not just on the device architecture scale, but also on the microscopic scale, how we can use novel particle morphologies, novel chemistries to design better electrodes. I mentioned previously that imaging is key to understanding some of the microscopic phenomena occurring within these devices. So we take tomography data, for example, of an electrode from a lithium-ion battery cathode, and by combining that data, for example, with CFD or finite element simulations, we can get insight into the transport properties in these electrode materials. This video is a fly-through video of exactly what the internal structure of one of these porous electrodes looks like. When we zoom out, hopefully the streamlines will become more apparent as to what they indicate. So this scale bar is 10 microns. So this is a cube of material about 7 microns across. By using image-based modeling, we're able to image the streamlines for, in this case, a pressure-driven flow in the porous medium, and color them according to their relative contribution to the pressure-driven flow throughout the material. In doing this, we're able, on a very small microscopic sample, we're able to link the microscopic structure to its expected transport properties. And again, by using this in tandem with more established bulk material characterization techniques, we're able to link that overall to a device-level performance. I wanted to finish by just giving a couple of examples of some research that, as I've said here, is hot off the press, some recent research highlights. The first is in extending the capability of X-ray imaging to look at very low atomic number materials. Obviously, we're interested in lithium batteries. Lithium is the least dense metal and therefore is inherently extremely challenging to image using X-ray imaging because the X-rays just shoot straight through it. Typically, we're using X-ray imaging, historically in material science, to image aluminium and iron and steels and so forth. When we're down at the very bottom end of the periodic table, it's a real challenge to get any contrast with the imaging technique and to be able to reconstruct anything meaningful from the data. We've worked extensively at UCL with Diamond, Manchester University and the University of Cambridge in developing new imaging techniques in order to be able to characterize this lithium metal structure for the first time. And we're interested in this predominantly because now we can characterize the formation in situ of lithium dendrites. So these lithium dendrites are a well-known but poorly understood failure mechanism which causes short-circuiting in lithium-ion batteries. And for the first time, we can image how these dendrites form in situ. This is leading us to strategies for dendrite minimization and also to ideas for improving the strengths of separator materials to prevent the short-circuiting phenomena that I mentioned. The next example is some real-time failure radiography. This is an image of the side plane of one of these Swiss roll or jelly roll cells, another 18650 cell. This was taken at 1200 frames a second using extremely high brightness synchrotron radiation at the European Synchrotron Radiation Facility in Grenoble. What we're seeing here is a number of electrode layers, and we're inducing a thermal runaway. In the radiograph, we can see that during this thermal runaway process, we have this initiation of the thermal runaway at the central core of the cell, and we can image these black blobs here of the melting copper that's being taken up and ejected out of the top of the cell. By contrast, the outside skin of the cell, which was the original thermal image that I showed on the very first slide, is about 200 degrees centigrade. So we have a thermal gradient from about 200 degrees centigrade on the skin to over 1,000 degrees centigrade in the center of the cell where we're able to visualize the copper melting. And of course, we can do this in 3 dimensions as well to analyze the effects on the overall device architecture as a post-mortem analysis tool. I'm conscious of the fact that I'm probably close to my allotted time, so just to briefly conclude, I hope I've shown you that X-ray microscopy provides us a valuable tool to understand these lithium-ion batteries from the atoms to the device length scale, and as we take this research forward, we're aiming to do things faster, at higher resolution, and in doing so inform new designs both of devices and materials. The Royal Academy of Engineering Fellowship has been a fantastic scheme for me and has enabled me to travel around the world using some of the world's best and brightest synchrotron facilities in the US, Switzerland, France, and here in the UK at Diamond. I'd like to just finish by acknowledging my collaborators at universities, companies, and national labs all around the world. Of course, the Royal Academy of Engineering for their funding, and thank you all for listening today.
Thank you, Paul, for that fascinating insight. If my warning earlier about switching phones off didn't make people switch their phones off, that certainly did. I noticed a lot of people hurriedly checking whether their phone was getting hot, so thank you for that. We're going to move on. I should have explained at the outset the format. We're going to take Q&A at the end of both speakers, a short session before we break for coffee. So I'm going to invite now our second speaker to the platform. That's Professor Dino Distefano. He's a former Royal Academy of Engineering Research Fellow. His fellowship finished last year. And he's currently software engineer at Facebook and a professor of software verification at Queen Mary College. His speciality is mathematical theory called separation logic, and he co-founded in 2009 a company called Monoidics Ltd, and it was a high-tech startup, sufficiently successful that it was bought by Facebook in 2013. I should also congratulate Dino. He was this year one of this year's recipients of the Royal Academy Silver Medal. So, fascinating title for Dino's talk is Software Verification for 1 Billion People. So, Dino.
Thank you. Right. Thank you for inviting me. It's really a pleasure to give this talk today. So what I'm going to talk about is the work that I've been doing in the last few years in trying to bring some very theoretical ideas in mathematical logic up to some practical work that can be used in to to improve and software that is used by many people. So at the moment, let's say for 1 billion people. Of course, work like this is not done by one person only. During the years, I've been collaborating with many people. And in particular, the work that I'm going to present today has been done in collaboration with Cristiano Calcagno, Peter O'Hearn, and Honsak Young. And of course, I would like to thank also the Academy for the fellowship that I had a few years ago, and that helped me quite a lot in the work that I'm going to present today. Okay, so let me start with this ad. So I think many people in this room have seen this ad. It was one of the first ads about mobile phones. And that would say, like, there is an app for that. This is basically true. Whatever we do nowadays, we can go and check, and there is an app that helps us to do that. So traditionally, what we've seen is like critical software has been considered the one that actually goes on planes and power plants, cars. And of course, this is true. But recently, we see that more and more of the software that we use nowadays for common use is becoming more critical for all of us, because we start to do many activities that are critical for all of us. So like we take our phone, we take some app, we just connect to our bank, we move money and do things like that. And those are activities that we do every day, and they are increasing more and more. It's also interesting to see is like the scale of this, how this is becoming common. So up to the end of 2013, there were 800 million Android phones active, and 300 million iPhones. So by now there will be many more. And so we have a lot of highly used software out there in all our phones, our laptops, and so on. But this kind of software is shipped with many critical errors. So what I've been working in the last several years has been like a technique called automatic software verification. And this technique aims at building something called a verification system. There is a system that takes an input on one side, a piece of software, and on the other side, a property that we want to check for that software. And then the system will make some kind of mathematical calculations, and it will say yes if it can prove that actually the software satisfies the property that you want to check. Or it might say no and give you a reason why this is not the case, so it's going to give you a counterexample. Or it might say, I don't know, just because software verification is one of the undecidable problems, so it cannot be answered in any possible instance. So sometimes you might not have a way to calculate and in an automatic way an answer to this question. So in terms of the property that you might want to check for your system, might be like functional correctness. That would mean that you want to check if the software does what it's supposed to do, so if the design is correct. Or you might check for something slightly easier. That is like you might want to check that the software is not going to crash. This is easier than the previous kind of property, but it's still very important because in many situations you want that your software is not going to crash. Sometimes you might also be interested in, say, your software is not leaking information in the outside world. Okay, right. So the kind of program analysis I've been focusing in the last years has been something about like dynamic data structures. When I start my Royal Academy of Engineering Fellowship in 2006, there were theoretical techniques that could be applied to this kind of software using dynamic allocated data structures. But you could only do things like very small programs, toy programs like 100 lines of code. But in reality, the real world is full of these programs that we use every day, and they're huge programs. So there was a kind of gap between the theory and the real world. And then what I said, I remember in my in my interview for the fellowship, I said like my plan for this fellowship is like to bridge this gap between this theory here and the real world out there. We want to prove programs that everybody uses. I want to point out that this kind of analyzing this kind of programs that use dynamic data structures is pretty difficult because it's kind of technical. It's very difficult to make them scale because it's a very complex kind of structure to reason about. So it has been a problem that many people have been looking at, and it's quite hard. And in fact, Sir Tony Hoare, a Turing Award, he said in 1973 that pointers, which are this kind of structures that this kind of program use with dynamic structures, are a kind of the introduction of this pointer in high-level language has been a step backwards from which we might never recover. That's what he said in 1973. And it's true because you see, like, what we're trying to reason about is this kind of picture over there with a piece of memory that actually can reference to each other in a very crazy way. And this picture would change while the program is running. And so what you need to do is try to find some kind of mathematical way to reason about this kind of evolution of this kind of pictures over there. So how do we do this? Okay. Basically, what we do, we specified the properties that we want to prove in mathematical logic. And in particular, we use one special kind of mathematical logic called separation logic that was invented by John Reynolds and Peter O'Hearn in the 2000s. And the reason why we use that is because basically this kind of logic simplifies the way we can reason about systems that use this kind of dynamic data structures and pointers. In particular, if you see this picture here, you will see that this is a proof that a program of 3 lines of code, like the one I highlighted in yellow, it doesn't go wrong. Now, you can see that you have like 3 lines of code and a lot of math around it. So it was very difficult to make this kind of reasoning, this kind of proofs. However, with the advent of separation logic, you can do the same in a much easier way. So now you can see that the other pictures show the same kind of proof in a more concise way. So we thought that this is like a good theoretical tool that we can use to try to automate the kind of reasoning we want to do and produce automatical tools to make this kind of reasoning. All right. So let me tell you a little bit more about what a verification system is. So basically, what it does is like is a system that actually represent internally the state of a computer program using these formulas in separation logic. Then what is happening is like the system is going to manipulate those formulas to simulate the way that the program will have while running. While running. So basically, in this way, by this manipulation of formulas, is trying to compute all the possible states, all the possible situations where the program will be while running in reality. Now, so you need to do all this computation just before. So this is like the program is not running. It's just all this number of states are calculated before the program is run itself. So, and this is a kind of huge amount of possible states that can happen. So one difficult part in this kind of technology, in developing this kind of technology, is like you need to design highly sophisticated abstractions that allow you to make the reasoning easier, but still precise enough for getting good results out of this kind of analysis. Now, we have been like designing this kind of abstractions for several years because this was one of the most difficult thing, trying to find kind of good abstraction that would be able to give us like a way to reason in a kind of efficient way for this kind of evolution of the system. Now, we reached a point where we had like very good abstraction that could actually analyze very complicated program. And in fact, I remember like we reached a point where we could analyze a complete industrial program of 10,000 lines of code. Now, this was a kind of like a big hit in the community working on this area, because it was like the first time it was done. However, what I was thinking at the time, it was like, well, this is still not enough. I mean, if we want to do verification for real, we really want to give some tools to our developers that they can actually use. And for them to use something, it should be really automatic, and it should scale at the level of software that they're writing. So this is the situation that we were a few years ago now, when we managed to do this proof of this 10,000 line of code. So we got some code, and we work on it for like a few months or a few weeks. And in order to massage this code, improve our analyzer and so on, at some point we could push a button, and then we will have, like, after a while, some results about this code. But this is not the way that a software engineer works nowadays. And it's something different. The situation would be more, what we want is something more like that. So, like, we need some tool that actually you get the code, you can immediately press a button and analyze your code. And by the way, the code that people write nowadays goes on the millions of lines of code. It's not anymore this kind of 10,000 line of code now is pretty small. So it was clear that we were not there yet. We were in a good position, but not there yet. So it was clear that we need a different approach. And so we decided that the right thing we need would be like to use compositionality. Compositionality in the sense of the Frege principle in semantics of language. So Frege would say that the meaning of composite expression is determined by the meaning of its constituent parts. So we want to have a similar kind of principle in program analysis and verification. So what we want to have something like the analysis results of a composite program is computed by the analysis result of its parts, so that we can do like smaller things and scale at a bigger scale. So just to picture that, so if we will have like a big program composed by many different parts, we want to have like ways to make little analysis of little parts and then start to compose them, so that we can reach the point where we can have like a big analysis without trying to do the big analysis since the beginning, because that was what we were doing before. It was not scaling up to a certain kind of point. Okay? Now, compositionality is a principle that people in computer science have been using for quite a while. The question was like, how do we do it in our case? Because it was not clear how we could do that when we're trying to analyze dynamic data structures and pointers. So this was the big difficulty. And yeah, so at some point, what we discovered is like a good recipe for achieving that is actually using something that goes back to philosophy of science. It's called abducted inference. It's a notion in logic that was introduced by Charles Peirce in the beginning of 900 when he was writing about the scientific method. So abduction is like the principle of coming up with new hypotheses that can explain as a new, a strange phenomenon. So that's what basically Peirce was saying, like when a scientist see, say, a surprising phenomenon, what it does is come up with some hypothesis, and then we try to use deductive methods to see if the hypotheses are correct and they are able to explain the phenomena that he wants to do. They want to explain. So now we realized that what we need is something similar. So what we did, we code, or we kind of adapt this principle of abducted inference in our system, so that it could come up with, synthesize automatically some hypotheses that can help to actually make proofs of smaller parts of the program. And then by having those kind of little proofs, they compose them together and get this principle of compositionality. This is where we kind of got like kind of two things at the same time: scalability, because we could use compositionality, and automation, because at this point there was no manual work to do anymore. Hypotheses were kind of synthesized automatically by this kind of system that would implement this old principle. Okay, so, and when we got there, then it was quite interesting, because then we could actually scale, our analysis would scale on large programs. So from several, say, from say 100,000 lines of code up to millions of lines of code, like an Android system. And this was like kind of very interesting, because it was the first time that this was done. And then when we did that, then we got a lot of new kind of bugs that were not known before in open source software that have been running for quite a while. So this was kind of pretty interesting and nice for all of us. And so at that point, we said, like, okay, so maybe a good thing to do is like to try to commercialize this kind of technology. So we set up a company called Monoidics for developing a commercial version of this kind of technology. So, and Monoidics was actually bought by Facebook 1 year ago. They were interested in the use of this technology for improving the quality of their mobile software. And so nowadays, this kind of technologies run every day, more than once a day, let's say, on this kind of software. So it improves the way that, on one side, the way that developers do their job, so it helps them to actually do a better job, and on the other side, help for all the users to have like a better experience, because they have like more reliable systems. So let me conclude. Just want to say that well, I mean, it's kind of nice like to see like a very theoretical ideas like mathematical logic, abduction, compositionality, get to the point where they can be used for improving software that is used by over 1 billion people every day. And yeah, I mean, something that we couldn't foresee many years ago, but it's quite nice to see today. Thank you very much.
Wherever you like. So thank you, Dino, for a very clear description of a fairly complex topic. Very topical at the moment. Some of you may have read in your paper this morning that a few little problems with Apple's latest operating system wiped a few $1 billion off the value of the company yesterday. So very topical that software is properly validated before it's let loose on the user. We're running a little late, but I would like to give you a chance to ask just one or two questions of our first two speakers this morning. So who wants to start the ball rolling? Okay, gentleman in the middle. Just wait for the microphone to get to you, and if you would state your name and affiliation before asking your short question.
Graham Marshall, University of Bristol. Dino, having all this information must be very empowering. At the same time, you know, developers are facing now huge numbers of bugs which they hadn't seen before. How do you reconcile knowing where all the points of failure are in a piece of code and then managing that in terms of getting your code out there in a timely fashion?
I think there are different kind of systems that can be built, right? There are companies like Facebook that tend to ship their code pretty quickly, and very often to improve it all the time by using all sorts of different kind of tools. And this is kind of different kind of way of working, for example, like companies that build, I don't know, airplanes, where you need to have a different kind of design, and you will ship your product in 20 years' time. So I don't know if this answers your question, but.
Thank you. Next question? Yes. Vincent.
Yes, Dino, good morning. Vincent Mifsud from Cobham. One of the things I didn't quite appreciate is how this fits in with other tools. Are you saying that your approach finds every fault, or does it help to get to a fault-free code?
No, I don't say that this approach finds all the bugs. This would be impossible. It finds certain category of bugs, and so in this way improves the quality of the software. But it would be crazy to say that it would eliminate those bugs.
Other question? He's desperate. Yes, there we are. Desperate for their coffee.
Hi. Oliver Payton from the University of Bristol as well. This is a question for the X-ray tomography. Is there something that the X-ray tomography doesn't tell you about the sample? Is there something extra that you'd like to know about your sample that you're not able to get from that technique?
Yeah, absolutely. I mean, it tells you a lot, but it doesn't tell you everything. I think that typically it will tell you structural information more than it will tell you chemical information, more than it will tell you anything about the kind of coordination number of any of the atoms that are within the structure. And it's also, you're doing most of the resolutions as discrete experiments, so it's not necessarily a continuous linkage between all the different resolutions, even when you're looking at imaging. So we work with a number of different spectroscopy tools, from those that are within the lab, a number of different microscopy tools, including electron techniques as well as X-ray techniques. And at a synchrotron, increasingly, we're able to do coupled imaging in spectroscopy. So, for example, doing X-ray diffraction to get the chemical information at the same time as you're doing X-ray imaging to get the structural information, or XAFs in order to get some information about the coordination of the atoms. So it's, in fact, Diamond is impressively leading the way with a number of these new kind of combinatorial techniques to the new machines that we're building look like Christmas trees because they've got so many different branches coming off of them. But for example, the dual imaging and diffraction beamline that's being built at Diamond will be absolutely world leading to keep on adding to the information. So it's not just images, it's chemistry, it's crystallography, etc. at the same time.
It's really interesting. Thank you.
Have you had a chance yet to look at any of the lithium air batteries that are starting to appear now?
Yes, we have done a little bit of work with the lithium air. There's challenges there because, again, you're looking at relatively low atomic number materials and often with very, very fine structures. But yeah, we have begun to dip our toes into lithium air water, but we have more experience actually with lithium sulfur, which we see as a closer battery to commercialization. And in fact, there are a few spin-out companies already, including some in the UK, for example, Oxys, who are beginning to make real sort of inroads into making practical lithium-sulfur batteries.
Good. One more question, then we'll break for... God, hundreds of hands going up now since I said one more. I'll take one here.
Spencer Shearing from Imperial College London. I guess it's a bit of a cheeky one. I have 100,000 lines of code that I would actually like to apply your software to. But how would I do that? Do you have open license versions? Or?
Can we discuss it later?
Get your checkbook out.
Is there intention in the more less cynical view to sort of our later discussions, how do you make impact? A lot of software in my own community has had to become openware in order to get usage. I mean, your model presumably isn't focused that way.
There are many tools, open source, that are pretty good for doing that. So now, at the moment, it's like, well, so our tool is not open source, but we can discuss this later.
On that note, I'd like to thank Dino and Paul and ask you to thank them. We'll break now for a coffee break.